In this lesson, we'll recall the quadratic formula, how to use it, and then apply it to solving an equilibrium problem in chemistry. Here's our example problem. Our first task is to calculate the initial concentrations of the reactants in units of molarity so that we can fill in our ice table. Here we've filled in everything we know from the problem setup. Next, we need to fill in the change line. Here we have our completed ice table. Our next task is to write the correct equilibrium expression for the reaction. Now that we have everything we need, it's time to start plugging in numbers so we can chug out an answer. I've added the equilibrium concentration of each species to the black equation. To get to the next step, listed here in blue, we need to FOIL out the terms in the denominator, or multiply the first terms, the outer terms, the inner terms, and then the last terms. Then we collect like terms, those terms that are raised to the same power of x. This gives us the green equation. Next, we need to clear the denominator, which we can do by multiplying both sides by the denominator to get the purple equation. Finally, we have to distribute 4.10 times 10 to the negative fourth to each of the terms in the purple equation. Mathematically, this got ugly pretty fast. So let's take a minute to think about how we can solve for x in the red equation. Once we rewrite our equation in standard form, we can use the quadratic formula to solve for the two roots, or solutions, of x. Standard form means that the terms are written in decreasing powers of x, all set equal to 0, and we want to make sure that the leading coefficient a is positive. If you have trouble recalling the quadratic formula, I found this mnemonic to help you remember it. Now, a word of caution here. Only use graphing calculators or web-based calculators to check your work. You must be able to do these calculations using only a basic calculator on the homework and on the exam. Okay, so let's go back to our equilibrium problem. I've repeated our red equation from the previous slide here, as well as the standard form for the quadratic equation in the box. Next, I've flipped the equation to get the 4x squared term on the left-hand side. Then I used algebra to get the equation in standard form, with all of the terms collected on the left and written in descending powers of x. This gives us the blue equation. Now it's time to drop this information into the quadratic equation so we can solve for x. Here's the quadratic equation put into practice. First, I dropped the values of a, b, and c into the equation. Then I multiplied everything out. At this point, I noticed I could make a quick simplification here because 7.77 times 10 to the negative 8th is so much smaller than 7.05 times 10 to the negative 4th. I saw that the 10 to the negative 8th term would get lost in the sig fig rounding anyway, so why not just eliminate it here and save ourselves some complications. Crossing out this smaller term, we quickly arrive at the simplified equation at the bottom of the slide. At this point, it's time to split this equation up to solve for both values of x. Here I've separated the values of x into the plus and minus expressions, solving for my final two roots, or possible values, of x. Now we have to decide which root makes sense. If you get a negative value for x, that's definitely not the right answer. Negative concentrations do not make sense. For the same reason, if you get a positive x value that you plug back into the ice table and it results in a negative concentration in the equilibrium line, that answer also does not make sense. Using the correct value of x, listed here, what are the answers to the original question? Make sure you were able to fill in the final line of the table correctly. If you couldn't, please work with your study group to troubleshoot your technique or visit the Learning Center for additional assistance.